The cosmos is built by forces we can never see. An invisible architecture of dark matter, dark energy, and quantum fields directs the motion of galaxies and dictates the ultimate fate of everything. Carl Sagan once said the cosmos is within us, that we are made of star stuff. This journey will show you exactly how those unseen architects shape our existence. By the end, you will see the universe not as a random void, but as a carefully woven tapestry whose threads are hidden from our eyes. How did the faintest quantum whisper after the Big Bang grow into the grand cosmic web we observe today? And what does the accelerating push of dark energy mean for our distant future? When you look at the night sky, what do you feel is truly holding it all together? Our universe moves with the rhythm of a grand symphony. Stars and galaxies swirl in an immense dance, yet the conductors of this performance remain entirely unseen. These are the hidden architects of the cosmos, the fundamental forces and entities that sculpt the universe from behind the veil. Physicist Brian Greene captured this perfectly, noting that the universe is a place of both grandeur and subtlety, where the most powerful influences are often the least apparent. These architects, like dark matter and dark energy, are nothing like the atoms that build our world. They operate in a realm beyond our direct sight, yet they command the gravitational pulls that bind galaxies. They set the tempo of cosmic expansion, and they drafted the blueprint for the vast cosmic web. Their story began not with a direct sighting, but with a puzzle. Astronomers noticed that galaxies were spinning so fast they should fly apart, yet something unseen was providing the extra gravity to hold them together. Later, the faint afterglow of the Big Bang, the cosmic microwave background, revealed its own secrets, its patterns confirming the presence of this mysterious, invisible mass. One of the most striking proofs came from the Bullet Cluster, a cosmic collision of two galaxy groups. Observations showed that the visible matter, the hot gas, was slowed and tangled by the impact. But the majority of the mass, revealed by its gravitational lensing effect, had sailed right through, completely separate. This was a ghostly signature of dark matter, a clear demonstration of its tangible, physical power. How would our perception of reality shift if we could suddenly see this invisible scaffolding holding our universe together? To begin answering that, we must first meet the most elusive of these architects. The evidence for this invisible hand was mounting for decades before it had a name. In the 1970s, astronomer Vera Rubin made a discovery that would permanently change our understanding of the cosmos. She was meticulously measuring the rotation speeds of stars within spiral galaxies, expecting the outer stars to move slower than the inner ones, just as Pluto orbits our Sun more slowly than Earth. But the data told a different story. The stars at the edges of galaxies were hurtling around at nearly the same incredible speed as those near the center. According to the laws of gravity, these galaxies were spinning so fast they should have torn themselves apart, flinging stars into the void. The only logical explanation was that they were held together by a tremendous amount of unseen matter, a gravitational anchor we could not see. This was the first robust clue for what we now call dark matter. Cosmologist Laura Mersini-Horton describes dark matter as the cosmic glue that binds galaxies, preventing them from flying apart. It is a mysterious, non-luminous substance that makes up roughly 27% of everything in the universe. It does not absorb, reflect, or emit any light, making it completely invisible to our telescopes. Its presence is known only through its gravitational pull, a fundamental force it exerts on the things we can see. But what is it made of? The leading candidates are exotic particles that barely interact with normal matter. One possibility involves weakly interacting massive particles, or WIMP, heavy particles that would only rarely bump into a proton or electron. Another candidate is the action, a theoretical particle that is incredibly light but could exist in vast numbers. These particles are thought to form immense, diffuse halos around galaxies, vast spherical clouds that envelop the visible stars and gas. This dark matter halo is what sculpts a galaxy's rotation curve, creating the flat, high-speed spin that Vera Rubin observed. Its gravitational influence is also dramatically revealed through a phenomenon called gravitational lensing. The immense mass of dark matter warps the very fabric of space-time around it, bending the path of light from even more distant galaxies. Astronomers see these distant objects stretched and distorted into faint arcs and rings, a clear signature of the invisible mass in the foreground. This effect is written into the oldest light in the universe, the cosmic microwave background. The subtle patterns in this afterglow show the gravitational footprints of dark matter, pulling on the hot plasma of the infant cosmos and seeding the structures that would later become galaxies. Consider our galactic neighbor, the Andromeda Galaxy. Its beautiful spiral arms are rotating at speeds that should unravel them, yet they remain stable and intact, held fast by a massive, invisible halo of dark matter that provides the extra gravity needed to keep everything in place. This unseen scaffolding is not unique to Andromeda. It is the rule for every large galaxy we have ever studied. So what if we could one day understand this substance so well that we could harness its subtle interactions? While purely speculative, the ability to manipulate dark matter could open doors to technologies we can scarcely imagine today. But to even approach that future, we must first understand how this invisible architect collaborates with its even more mysterious counterpart, a force that does not pull but pushes. Just as dark matter's gravity pulls the cosmos together, a second, more mysterious force pushes it apart. Think of the universe as a balloon, not just inflating, but one whose surface is stretching faster and faster with every passing moment. The breath filling that balloon is dark energy, the enigmatic force responsible for the accelerating expansion of the cosmos. It makes up about 68% of the universe's total energy, a dominant presence we cannot see or touch. Nobel laureate Adam Rees calls dark energy the biggest mystery in physics, a force causing the universe to expand at an ever-increasing rate. Its discovery in the late 1990s came as a profound shock. Two independent teams were observing distant supernovae, using these exploding stars as cosmic mile markers to measure how quickly the universe was expanding. They expected to find that gravity was slowing the expansion down. Instead, they found the opposite. The most distant supernovae were fainter than they should have been, meaning they were farther away than anyone predicted. The expansion of the universe was not slowing, it was speeding up. This was like throwing a ball into the air and watching it shoot away faster and faster, defying gravity itself. So what could possibly be causing this cosmic repulsion? One leading idea comes from Einstein's own equations, a term he called the cosmological constant. This represents a constant energy density smoothly distributed throughout the vacuum of space itself. It acts as a kind of anti-gravity, a persistent push embedded in the fabric of reality. Another theory proposes a dynamic energy field called quintessence, which could change over time. Unlike the attractive force of gravity that works to pull matter together, dark energy operates on the grandest scales, creating a negative pressure that stretches space itself. It is uniformly distributed, meaning every cubic inch of the vacuum of space, from the void between galaxies to the emptiness in your living room, contains this same repulsive energy. This connects to the mind-bending concept of vacuum energy, where quantum mechanics suggests that empty space is not truly empty, but seethes with virtual particles flickering in and out of existence. Could the collective energy of this quantum foam be the source of dark energy's push? The consequences are staggering. Look at the Hubble Space Telescope's deep field images, which reveal thousands of galaxies. Each of those galaxies is being carried away from us by the stretching of space, and that recession speed is increasing. If this acceleration continues unchecked, dark energy dictates a cold and isolated future known as the Big Freeze. Over trillions of years, galaxies beyond our own local group would be pushed away so far that their light could never reach us, leaving our descendants with a sky nearly devoid of galaxies. How does the idea of an accelerating universe, driven by an invisible energy we do not understand, challenge our deepest notions of eternity and end? This relentless push, however, may have its origins in the smallest of scales, in the quantum realm where the rules of reality are rewritten. Even the emptiest void in space is not truly empty. Place two perfectly smooth, uncharged metal plates extremely close together in a vacuum, and something strange happens. They are gently pushed toward each other by an invisible force. This is the Casimir Effect, a tiny but measurable push caused by the quantum nature of reality itself. The space between the plates is so narrow that it restricts the kinds of quantum fluctuations that can exist there, while outside the plates, a sea of unrestrained energy pushes inward. This is our first direct clue that what we call nothing is actually a vibrant, dynamic arena. The great physicist John Wheeler described the vacuum as a boiling sea of virtual particles, not nothingness but a dynamic arena. This quantum vacuum is the most fundamental substrate of the cosmos, a seething ocean of energy where particles and their antiparticle counterparts constantly flicker into existence and then annihilate each other almost instantly. They are permitted to exist by Heisenberg's uncertainty principle, a fundamental rule of quantum mechanics that allows for brief violations of energy conservation. Think of it as the universe allowing for a tiny, short-term loan of energy, as long as it is paid back incredibly quickly. These virtual particle pairs are everywhere, popping in and out of the void in an endless, frenetic dance. Their fleeting existence is not without consequence. This ceaseless activity gives the vacuum a baseline energy, known as zero-point energy, and it is this energy that may be the engine behind the largest-scale phenomena. During the first fraction of a second after the Big Bang, a period known as cosmic inflation, it is believed that a similar form of vacuum energy caused the universe to expand exponentially, stretching a subatomic speck to a macroscopic size in an eye blink. Today, many cosmologists theorize that the same fundamental process, the energy of the quantum vacuum, could be the source of dark energy, driving the accelerated expansion of the universe we observe now. The influence of these subatomic architects even reaches the edge of oblivion. At the boundary of a black hole, a virtual particle pair can pop into existence. Normally, they would annihilate each other and vanish, but if one particle falls across the event horizon while the other escapes, the black hole loses a tiny amount of mass in the process. This is Hawking radiation, a theoretical prediction that black holes are not entirely black but slowly evaporate over eons, all because of the relentless activity of virtual particles. So if the vacuum of space holds such immense, untapped energy, could we one day learn to harness it? The ability to extract even a fraction of this quantum power could revolutionize everything, from propulsion for interstellar travel to the very way we power our world. To understand if that is even a remote possibility, we must trace this thread of influence back to the very beginning, to the moment the first quantum whisper dictated the destiny of everything. The universe was born in a firestorm of exponential change. Within the first fleeting fractions of a second, a remarkable event called cosmic inflation took a subatomic speck of primordial reality and stretched it to a size larger than our entire observable universe. This was not a violent explosion, but a sudden, smooth, and incredibly rapid swelling of space itself. Physicist Alan Guth proposed this theory to solve deep cosmic puzzles, suggesting that a peculiar energy field, the inflaton field, drove this breathtaking expansion. What began as the tiniest of quantum tremors in this field were stretched to astronomical proportions, becoming the seeds for all future structure. As physicist Andre Linde explains, inflation turns microscopic quantum jitters into the galaxies and clusters we observe. Those minute fluctuations in density, these quantum wrinkles, were imprinted onto the fabric of the cosmos. They became the blueprint, the subtle pattern of slightly denser and slightly emptier regions that would later dictate where galaxies would form and where vast cosmic voids would reside. This primordial signature is written in the oldest light we can see, the cosmic microwave background. Space telescopes like Planck have mapped this afterglow with exquisite detail, revealing a faint, mottled pattern of hot and cold spots. These anisotropies are not random. They are the fossilized imprint of those initial quantum seeds, magnified by inflation to cover the entire sky. The theory also elegantly solves two great mysteries. The horizon problem asks why the universe looks so uniform in all directions, as regions now far apart could never have been in contact. Inflation answers this by stating they were once close together before being stretched apart faster than light. The flatness problem questions why the geometry of our universe is so perfectly balanced between open and closed. Inflation predicts this precise flatness, a prediction that subsequent observations have powerfully confirmed. Experiments like BICEP-2 have scanned the cosmic microwave background for a specific curl, a pattern called B modes, which would be the smoking gun signature of primordial gravitational waves rippling through the infant universe during inflation. While definitive proof remains elusive, the search continues, probing the energy scales of the universe's very first moments. What if we could trace the galaxy cluster you see in a telescope image directly back to a single, specific quantum fluctuation that occurred in that first unimaginable second? To complete that journey, we must follow the gravitational force that sculpted those seeds into the grand cosmic architecture we see today. An apple falling from a tree gave Isaac Newton a profound insight that the same force pulling fruit to the ground also guides the moon in its orbit around our planet. This was gravity as a simple, predictable pull between masses, a force that could be calculated and understood. But centuries later, Albert Einstein saw something deeper at work. He realized that gravity is not a force in the traditional sense, but rather the curvature of the cosmos itself. His theory of general relativity revealed that mass and energy warp the very fabric of space and time, creating what we perceive as gravity. Einstein famously summarized this cosmic relationship by saying, "Matter tells spacetime how to curve, and spacetime tells matter how to move. Imagine the universe as a vast, taut rubber sheet. Placing a heavy bowling ball in the center creates a deep depression. Now roll a marble nearby and its path will curve, orbiting the larger mass. This is the essence of gravity. Objects follow the contours of curved spacetime, paths known as geodesics. This curvature is the invisible architect of cosmic motion, dictating the elegant orbits of planets and the bending of light itself. One of the foundational ideas behind this is the equivalence principle. Einstein realized that a person in a windowless elevator accelerating upward through space would feel the same force as someone standing stationary in Earth's gravitational field. This led him to understand that gravity and acceleration are indistinguishable, a key step toward his theory of curved spacetime. This warping of space has been spectacularly confirmed in the modern era. When two black holes collide, they send ripples through the fabric of spacetime, vibrations known as gravitational waves. In 2015, the LIGO Observatory detected these waves for the first time, observing the specific chirp from a black hole merger over 1 billion light-years away. This was direct evidence of spacetime itself ringing like a bell. The most extreme warping occurs around black holes, where spacetime is curved so severely that not even light can escape. But the effects are also visible on the grandest scales. The immense gravity of a galaxy cluster acts as a gravitational lens, bending the light from more distant galaxies behind it. We see this as stretched arcs and multiple shimmering images of a single quasar, a perfect demonstration of spacetime acting as a cosmic lens. This same gravitational hand is what shapes the vast, invisible halos of dark matter, providing the scaffolding upon which galaxies are built. Without this curvature, there would be no galactic clusters, no cosmic web, no structure at all. So how does this fundamental sculptor, which orchestrates the grandest structures, interact with the other hidden architects, the quantum fields and dark energy that also vie for control of the universe's destiny? These invisible gravitational threads weave the cosmos into a single, immense structure. Picture the universe not as a random scattering of stars, but as a colossal spider's web, with galaxies strung along vast, interconnected filaments. This is the cosmic web, the largest pattern in existence, and its architecture is built almost entirely by the unseen hand of dark matter. Cosmologist J. Richard Gott described this web as the skeleton upon which galaxies are hung, built by dark matter's unseen hand. Its gravitational pull is the master sculptor, organizing all visible matter into a breathtaking network of dense clusters, wispy sheets, and staggeringly empty voids. Without this dark framework, galaxies would be adrift in a formless sea, never coalescing into the grand communities we observe. We have never directly seen this web, but we can map its shadow through sophisticated computer simulations. Projects like the Millennium Run model the evolution of the universe, starting with the faint seeds imprinted by inflation and letting the laws of physics play out over billions of virtual years. The result is always the same, an intricate cosmic lace where dark matter forms an invisible scaffolding. Within this structure, dark matter halos act as gravitational wells, deep pits in the fabric of spacetime where ordinary or baryonic matter can gather. Think of these halos as cosmic seed crystals. Vast clouds of hydrogen and helium gas, the building blocks of stars, are pulled in by this relentless gravity. They swirl, condense, and eventually ignite, giving birth to the brilliant galaxies that trace out the web's luminous outline. This process builds up structures of immense scale. Our own Milky Way resides within a supercluster of galaxies now known as Laniakea, a Hawaiian word meaning immense heaven. This structure is a single, sprawling filament of the cosmic web, containing over 100,000 galaxies, all moving under the collective gravitational influence of the dark matter backbone. Yet for all this structure, the web is defined as much by its emptiness as by its nodes. The distribution of dark matter creates profound deserts between the filaments. One of the largest known is the Boötes void, a spherical region of space nearly 330 million light-years across that contains remarkably few galaxies. It is a cosmic vacuum, a place where the dark matter density is so low that normal matter simply had no gravitational reason to collect. What does this intricate cosmic web, with its vibrant cities of galaxies and its silent, empty voids, tell us about the universe's fundamental design? It reveals a cosmos that is deeply structured, yet mostly invisible, governed by a substance we cannot see. This hidden architecture, however, is subject to other invisible forces, including immense magnetic fields that flow along the web's very filaments. Deep within the Crab Nebula, the remnant of a star that exploded nearly 1,000 years ago, a rapidly spinning pulsar unleashes a wind of charged particles. This storm is sculpted into intricate, swirling patterns not by chance, but by an immense, invisible magnetic field. The lighthouse-like beam of radio waves we detect from that pulsar is itself guided by these cosmic forces. Across the galaxy, and indeed throughout the entire universe, space is threaded with magnetic fields. They are the silent guides of interstellar space, pervasive forces that shape the dynamics of gas clouds, steer the birth of stars, and channel immense jets from the hearts of galaxies. Astrophysicist Ethan Siegel described them perfectly, calling magnetic fields the universe's invisible railroads, channeling energy and matter across light years. But where do these vast, invisible structures come from? Some may be primordial, faint seeds imprinted in the universe's earliest moments and stretched to cosmic scales by inflation. Others are generated continuously by dynamo effects, where the churning motion of charged plasma in stars and galaxies acts like a giant generator, amplifying weak fields into powerful cosmic currents. These fields exert their influence on anything with an electric charge. They align dust grains in space. They guide and accelerate cosmic rays, which are high-energy particles racing across the galaxy, and they shape the very clouds where new stars are born. We cannot see magnetic fields directly, but we can detect their presence through the light they influence. One method involves synchrotron radiation, the light emitted when high-speed electrons spiral along a magnetic field line. The eerie glow of the Crab Nebula is largely synchrotron radiation, a visible testament to the powerful magnetic forces at work. Another technique, Faraday rotation, measures how a magnetic field can twist the direction of light's vibration as it travels through space, allowing astronomers to map these invisible lines of force across the galaxy. Their role is fundamental to star formation. Giant molecular clouds, the cosmic cradles for new stars, are supported against their own gravity by turbulent gas motions and magnetic pressure. Without magnetic fields, these clouds would collapse too quickly, forming a few massive stars in a frantic burst. Instead, the fields provide a supporting structure that slows the collapse, allowing the cloud to fragment and birth hundreds of smaller, longer-lived stars like our own Sun. On the most colossal scales, magnetic fields are essential near supermassive black holes in active galactic nuclei. They help launch and tightly collimate the spectacular jets of plasma that shoot out for thousands of light years. These jets are unimaginably powerful, and it is the magnetic field that acts like the barrel of a rifle, focusing that incredible energy into a narrow beam that can influence entire galaxy clusters. So if these invisible railroads so effectively guide and shape the normal matter we can see, could they also hold a clue to the dark matter we cannot? Is it possible that dark matter, through some subtle interaction, is also influenced by or even generates its own kind of cosmic magnetism? To explore that frontier, we must turn to another ghostly architect, one that trillions of which are passing through your body at this very second. Deep beneath the Japanese Alps, inside a chamber filled with 50,000 tons of ultra-pure water, thousands of sensitive eyes watch for the faintest glimmer of light. This is the Super Kamiok and Observatory, and its target is the most elusive traveler in the cosmos, the neutrino. On February 23, 1987, this detector and others around the world were struck by a burst of 24 of these particles, all within a span of just 13 seconds. They were messengers from a cataclysm, the supernova 1987A, located in the Large Magellanic Cloud. Their arrival, hours before the visible light from the explosion reached Earth, confirmed a fundamental prediction of astrophysics and opened a new window into the violent deaths of stars. Neutrinos are the universe's ghosts. They are elementary particles with almost no mass and no electric charge, which allows them to pass through entire planets as if they were not even there. Trillions are streaming through your body every second, coming from the sun, from distant cosmic explosions, and from the remnants of the Big Bang itself, yet you feel nothing. Nobel laureate Arthur B. MacDonald called them cosmic messengers, revealing processes from the sun's core to distant supernovae. Their near-total lack of interaction is precisely what makes them such powerful probes, allowing them to escape from the most dense and chaotic environments where light is trapped. In the first few seconds after the Big Bang, the universe was so hot and dense that neutrinos were constantly slamming into other particles. But as the cosmos expanded and cooled, roughly 1 second after it all began, they suddenly stopped interacting and flew free, decoupling from matter. This created a cosmic neutrino background, a relic sea of these ancient particles that still permeates all of space, a cooler counterpart to the cosmic microwave background. While we have not yet directly detected this specific background, its gravitational influence is written into the large-scale structure of the universe, subtly affecting how galaxies clump together. Their ghostly nature is further complicated by a strange quantum behavior. Neutrinos come in 3 distinct types or flavors: electron, muon, and tau. As they travel through space, they do not remain as one single flavor. They oscillate, morphing from one type into another. This very oscillation was what the super camiok and detector proved, demonstrating that these particles must have a tiny amount of mass, a discovery that forced physicists to revise the standard model of particle physics. Their most dramatic role comes in the heart of a collapsing star. When a massive star runs out of fuel, its core collapses into an incredibly dense neutron star. The energy released in this collapse is staggering, and 99% of it is carried away not by light, but by a tremendous pulse of neutrinos. This neutrino blast is now believed to be the primary engine that drives the supernova explosion itself, literally blasting the star's outer layers into space. The neutrinos from supernova 1987 did exactly that, delivering a clean, unfiltered signal from the heart of the explosion. This process is also crucial for creating the elements that make up our world. The intense flood of neutrinos in a supernova can bombard the outer layers of the star, helping to transmute nuclei into heavier elements. Every atom of gold in a wedding ring or iodine in your body was likely forged in such a cataclysm, with neutrinos playing a hidden but essential role in its creation. Could a fraction of the dark matter that holds galaxies together be made of a yet undiscovered, heavier type of sterile neutrino? The search for this hypothetical particle continues, an attempt to link one ghostly architect to another. How do these spectral particles, which can traverse a light year of lead without stopping, hold the key to the violent births of the very elements that constitute our existence? Their story of creation and destruction leads us inevitably to the most absolute cosmic voids, the domains of black holes. A black hole is the ultimate expression of gravity's power, a point where the cosmic rubber sheet is stretched into an infinitely deep well. These objects are often called cosmic vacuum cleaners, voraciously consuming any matter that wanders too close. Yet that metaphor is profoundly incomplete, for they are also cosmic engines and recyclers, reshaping spacetime and energizing entire galaxies. Stephen Hawking reshaped our understanding of them, stating that black holes are not the eternal prisons they were once thought. They leak energy and information. A black hole forms when a massive star, many times heavier than our Sun, exhausts its nuclear fuel. The outward pressure from fusion can no longer hold back the star's own immense gravity, and the core catastrophically collapses. If the core is sufficiently massive, no known force can stop the collapse, and it crushes down to a point of infinite density called a singularity. This singularity is shrouded by the event horizon, a boundary in space from which no light or matter can return. We can think of the event horizon as the point of no return, the black hole's one-way door. The gravity is so intense here that the escape velocity exceeds the speed of light. But black holes are not always silent. When they exist in a binary system with a normal star, they can pull material from their companion. This stolen gas does not fall straight in. It forms a whirling, superheated disk of plasma called an accretion disk, spiraling around the black hole like water going down a drain. Friction within this disk heats it to millions of degrees, causing it to glow brilliantly across the electromagnetic spectrum, from X-rays to radio waves. In some cases, the black hole's immense rotational energy and powerful magnetic fields funnel some of this infalling matter into narrow, incredibly powerful jets that shoot out from the poles at nearly the speed of light. These jets can stretch for thousands of light years, punching through interstellar gas and injecting enormous energy into the galactic environment. The stellar mass black hole Cygnus X1 provides a perfect example. It orbits a blue supergiant star, relentlessly siphoning off its stellar wind. This process creates a persistent and powerful source of X-rays, a beacon that revealed one of the first compelling candidates for a black hole in our galaxy. On a far grander scale, supermassive black holes, weighing millions or even billions of suns, reside at the centers of most galaxies, including our own Milky Way. When these monsters are actively feeding, they become the engines for quasars, the most luminous and energetic objects in the entire universe, capable of outshining 1,000 galaxies. The Event Horizon Telescope collaboration gave us our first breathtaking image of such a behemoth, capturing the shadow of the supermassive black hole at the heart of galaxy M87, a dark silhouette encircled by a fiery ring of hot, swirling gas. But Hawking's insight revealed that black holes are not completely black. Due to quantum effects at the very edge of the event horizon, they slowly evaporate, emitting a faint whisper of particles now known as Hawking radiation. Over trillions upon trillions of years, a black hole can theoretically lose mass and eventually vanish. This profound connection between gravity, quantum theory, and thermodynamics suggests that information about what fell into a black hole is not truly lost, but may be encoded on its event horizon, slowly released back into the universe as it evaporates. Their influence is also felt through ripples in spacetime. When two black holes spiral inward and merge, they unleash titanic gravitational waves, like the ones first detected by LIGO, shaking the very fabric of the cosmos. So if black holes can leak information and energy back into the universe, could they be doing something even more profound? How might these gravitational titans be seeding new universes, their singularities birthing entirely separate cosmic realities in an endless, bubbling multiverse? Our universe could be a single bubble in an endless cosmic sea of other realities. This is the Multiverse Hypothesis, a theory suggesting that what we call the cosmos is just one of countless universes, each with its own unique set of physical laws and constants. Cosmologist Max Tegmark expresses this by saying the multiverse idea suggests that all possible realities exist somewhere, designed by fundamental laws we cannot observe. This concept emerges naturally from two powerful pillars of modern physics: cosmic inflation and string theory. The theory of eternal inflation proposes that the rapid expansion of the early universe never truly stopped everywhere. Instead, it continues in a vast background space, with new pocket universes constantly budding off like bubbles in an expanding foam. Each of these bubbles could represent a separate universe, forever isolated from our own, where even the number of spatial dimensions or the strength of gravity might be completely different. Another version arises from the strange rules of quantum mechanics. The many worlds interpretation suggests that every time a quantum event has multiple possible outcomes, the universe splits, creating a branching tree of parallel realities. In one branch, a particle goes left, in another, it goes right, and both histories become equally real, playing out in worlds that can no longer communicate. String theory, a candidate for a theory of everything, adds another layer to this. It proposes that the fundamental constituents of reality are tiny, vibrating strings. The way these strings vibrate determines the properties of particles and forces. However, the theory allows for a staggering number of possible stable configurations, often quoted as 10 to the power of 500. This is the string theory landscape, a vast assortment of possible vacuum states, each corresponding to a different universe with its own distinct physics. This leads directly to the anthropic principle. Our universe seems miraculously fine-tuned for life. If the force of gravity were slightly stronger, or the cosmological constant a little larger, stars and galaxies could never have formed. The multiverse offers an explanation. We simply live in one of the rare universes where the constants are just right for creatures like us to exist and ponder our origins. Could there be any evidence for something so seemingly untestable? Some scientists look to the cosmic microwave background, the oldest light in the universe. Large-scale anomalies in this afterglow, like unexpected cold spots or strange alignments, could potentially be explained as bruises from collisions with other bubble universes in the distant past. While this remains highly speculative, it turns the CMB into a potential window into the cosmos next door. If an infinite array of universes truly exists, where every possible history is real, how does that reshape our understanding of destiny and our own choices? This profound question about causality and possibility inevitably draws our attention to another invisible architect, the river of time itself. A shattered glass never spontaneously reassembles, its fragments refusing to leap back into a pristine whole. This everyday miracle reveals a profound cosmic truth, the relentless one-way flow of time. This is the arrow of time, a fundamental property of our universe driven by a single, invisible architect, entropy. Physicist Sean Carroll explains that time's arrow is baked into the cosmos, guided by the second law of thermodynamics. This law states that the total entropy, or disorder, of a closed system always increases, moving from a state of delicate order toward one of ultimate chaos. Our entire universe is that closed system, and its story is written by this inevitable progression from the astonishingly low entropy state of the Big Bang to the cold, high-entropy fate that awaits all. Entropy is not mere messiness, it is a measure of probability. There are vastly more ways for a system to be disordered than ordered. A sandcastle is a temporary, improbable arrangement of grains, easily destroyed by wind and waves which scatter the sand into a far more likely, random state. The universe operates on this same principle. The initial conditions of the Big Bang were a state of incredibly low entropy, a highly ordered and dense configuration that has been unraveling and spreading out ever since. This gradient, this slide from order to disorder, is what gives time its direction and makes cause precede effect. It is the reason we remember the past but not the future, and why stars burn their fuel instead of spontaneously forming from scattered stardust. This cosmic drive toward disorder is the engine behind the most dramatic transformations. Consider the life cycle of a star. It begins as a vast, diffuse cloud of hydrogen gas, a state of relatively high entropy. Gravity pulls this cloud together, which might seem like it is creating order, but the process releases heat and radiation into space, increasing the total entropy of the universe. The star then ignites fusion, methodically crushing light elements into heavier ones, a process that again increases the overall disorder of the cosmos. When a massive star finally explodes as a supernova, it is a spectacular entropy-generating event, scattering newly forged elements across light years, creating the raw, chaotic materials for new stars, planets, and even life itself. Life is a localized phenomenon that seems to create exquisite order, but it does so by consuming energy and expelling waste, thereby contributing to the net rise in universal entropy. Black holes represent the ultimate victory of entropy within a localized region. They are not simple vacuums, they are entropy maximizers. A black hole's event horizon hides a staggering amount of disorder within its tiny volume, so much so that physicist Jacob Bekenstein calculated that a black hole's entropy is proportional to the area of its event horizon. When matter falls into a black hole, the entropy of that matter is effectively erased from our visible universe, but the black hole's own entropy increases dramatically to compensate, upholding the second law. This deep connection between gravity, thermodynamics, and quantum mechanics hints at a unified framework governing reality. So if entropy dictates the one-way street of time, could we ever find a loophole? The fantastical idea of reversing entropy to travel backwards in time remains a staple of science fiction, but it confronts the immense statistical unlikelihood of the entire universe spontaneously returning to a more ordered state. To explore the most extreme possibilities for manipulating spacetime, we must turn to the theoretical relics of the universe's birth, cosmic strings. The same grand unified theories that describe the fundamental forces predict the formation of cosmic scars in the fabric of reality. These are cosmic strings, hypothetical one-dimensional defects in spacetime that may have been forged during the universe's first moments. When the hot, dense cosmos cooled, it underwent a series of phase transitions, much like water freezing into ice. But when these transitions occurred unevenly across space, they could have trapped immense energy into incredibly thin, vibrating lines. These strings are not made of matter, they are pure wrinkles in the geometry of spacetime itself. Physicist Alexander Vilenkin described them as fossils from the universe's infancy, potentially weaving the cosmic web. A cosmic string would be a thread of concentrated energy, thinner than a proton but with the mass of a mountain range packed into every inch. If one exists, it would stretch across the universe in a perfectly straight line, a flaw in the cosmic diamond so dense that it would warp space around it. Anything passing near it would experience a unique form of gravitational lensing, where the background sky would appear duplicated, as if seen through a cracked lens. The string's immense tension and density would also cause it to oscillate violently, sending out faint ripples in spacetime, a steady stream of gravitational waves that could persist for eons. These vibrations are one of the key ways we might detect them. Precision instruments like pulsar timing arrays monitor the regular flashes from distant neutron stars. A passing gravitational wave from a cosmic string would minutely disrupt the timing of these cosmic metronomes, creating a distinctive pattern in the data. The search is on for this subtle, persistent hum woven into the fabric of spacetime. Their potential influence on the cosmos is profound. In the early universe, the gravitational pull of a network of these strings could have acted as a scaffolding, attracting dark matter and normal gas to create the first seeds of galaxies. They are a different kind of hidden architect, one that carves structure not with invisible matter, but with the sheer geometry of distorted space. This idea finds a fascinating parallel in string theory, where the fundamental building blocks of reality are not points but tiny, vibrating loops. Under the right conditions, these fundamental strings could have been stretched to astronomical scales during cosmic inflation, becoming the very cosmic strings we hope to observe. What if we could see these space-time scars directly, tracing their incredible lengths across the heavens? Such a discovery would be a direct glimpse into the universe's most violent and energetic first moments. It would confirm that the vacuum of space itself holds even more secrets, its energy capable of freezing into defects that shape the cosmos for billions of years. The most precise theoretical calculation in the history of physics is also the most spectacularly wrong. When physicists attempt to calculate the energy density of empty space using our best theories of the quantum world, they arrive at a number. Then they compare this to the value we actually observe from the accelerating expansion of the universe, a value driven by dark energy. The two numbers should be the same, but they are not. The theoretical prediction is larger than the observed reality by a factor of 10 to the 120th power. That is a 1 followed by 120 zeros. This colossal mismatch is known as the cosmological constant problem, and it represents the most glaring gap in our understanding of the universe. Physicist Leonard Susskind called the vacuum energy the most embarrassing number in physics, yet it might hold the key to our fate. So what is this vacuum energy? It is the energy inherent in the fabric of empty space itself, a product of the quantum fluctuations that constantly seethe in the void. According to quantum field theory, every point in space possesses a baseline energy, a zero-point energy that can never be removed. This energy is not nothing. It is a dynamic property of the vacuum, and it is this very energy that many cosmologists believe is the engine behind dark energy, the force accelerating the cosmos. This idea connects directly back to Einstein's cosmological constant, a term he inserted into his equations to represent a repulsive force embedded in space. He later called it his greatest blunder, but it may have been his greatest prescience. The problem is one of catastrophic fine-tuning. Why is the observed vacuum energy so incredibly tiny, yet not quite zero? For the universe to be habitable, this number had to be balanced on a knife's edge. If it were much larger, the universe would have ripped itself apart before galaxies could form. If it were slightly more negative, the cosmos would have collapsed back in on itself almost immediately. This fine-tuning seems like a miracle, and explaining it is one of physics' ultimate challenges. One proposed solution involves a theoretical concept called supersymmetry. This idea posits that every known particle has a heavier superpartner. The wonderful mathematical consequence is that the contributions of a particle and its superpartner to the vacuum energy could perfectly cancel each other out, bringing the net energy nearly to zero. The catch is that we have not found any evidence for these superpartners, meaning if supersymmetry is real, it must be a broken symmetry at the energies we can probe. Another, more philosophical approach is the anthropic principle. Within the vast landscape of a multiverse, most universes have a vacuum energy value that makes life impossible. We, of course, find ourselves in one of the rare universes where the value is minuscule and allows for our existence. While this provides an explanation, it moves the question from why this number to why this universe. The vacuum's energy also plays a starring role in the universe's very beginning. The theory of cosmic inflation suggests that a similar form of vacuum energy, associated with a field called the inflaton, powered the exponential expansion of the primordial cosmos. This leads to a startling possibility about the stability of our reality. Our universe might exist in a false vacuum, a metastable state that is not the absolute lowest energy configuration. Think of it like a ball resting in a small dip on the side of a much deeper valley. For now, it is stable, but a random quantum event could theoretically knock it out of its shallow bowl, sending it rolling down into the true vacuum below. This would trigger a bubble of true vacuum that expands at the speed of light, fundamentally altering the laws of physics within it and wiping out everything we know. Is the vacuum energy, this enigmatic force we cannot directly measure, the ultimate architect of the cosmos's end, destined to either tear space apart or suddenly annihilate it? This profound question about how nothingness shapes everything leads us to another. How did something, specifically all the matter we see, come from almost nothing in the first place? The primordial universe was a forge of perfect symmetry, a seething plasma where every particle of matter was mirrored by an identical particle of antimatter. When these twins met, they annihilated each other in a flash of pure energy, a process that should have left the cosmos with nothing but a fading glow of light. And yet, here we are in a universe filled with galaxies, stars, and planets, all made of matter. We are the evidence of a broken symmetry, the survivors of a cosmic war where 1 in every billion particles of matter somehow avoided destruction. This is the mystery of baryogenesis, the process that tipped the scales and allowed something to emerge from almost nothing. Physicist Andrei Sakharov outlined the 3 essential conditions required for this cosmic imbalance to occur. First, the universe needed a way to violate baryon number, a fundamental rule that seemed to decree that the total amount of matter must be conserved. Second, it needed to break the symmetries known as C and CP, which ensure that the laws of physics treat particles and their antiparticles identically. And third, these processes had to happen out of thermal equilibrium, meaning they occurred while the universe was expanding and cooling too rapidly to maintain a balanced state. One compelling theory for how this happened is called leptogenesis. This scenario involves the very same ghostly neutrinos we met earlier. It proposes that in the universe's first moments, extremely heavy, sterile neutrinos decayed asymmetrically, producing slightly more ordinary matter particles than antimatter particles through their interactions. This tiny bias in the leptonic sector was then converted into the baryon asymmetry we see today through a subtle process called a seesaw mechanism, where the immense mass of the sterile neutrinos forces the ordinary neutrinos to be incredibly light. Our most powerful particle colliders, like the Large Hadron Collider, are actively searching for the fingerprints of these processes, looking for any slight deviation in how particles and antiparticles behave that could explain our existence. The evidence for this primordial victory of matter is written across the sky. The cosmic microwave background, that fossilized light from the infant universe, shows a stunning uniformity, but its minute fluctuations are consistent with a model where matter was dominant from the very beginning, providing the gravitational seeds for all structure. The fact that we see no vast pockets of antimatter in the observable universe, no titanic annihilation frontiers where matter and antimatter galaxies collide, strongly suggests the imbalance was set globally at the dawn of time. What if, in some hidden void beyond our sight, an antimatter galaxy spins in perfect reflection, its stars and worlds built from mirror atoms? The profound silence of the cosmos suggests not, but the question forces us to confront how delicate our cosmic inheritance truly is. This delicate genesis, however, points toward the influence of even more fundamental architects, the scalar fields that may have orchestrated the entire event. A fundamental field of energy permeates every corner of the cosmos, an invisible ocean through which all particles must move. Think of it as a cosmic molasses, a persistent presence that resists the motion of certain particles, endowing them with the property we call mass. Without this interaction, the fundamental building blocks of reality would zip through the universe at the speed of light, never clumping together to form atoms, stars, or planets. These are scalar fields, the most fundamental of the hidden architects, and their most famous representative is the Higgs field. Physicist Peter Higgs described the Higgs mechanism as a hidden architect, giving substance to the building blocks of reality. This process works through a concept known as spontaneous symmetry breaking. In the searing heat of the early universe, the Higgs field was in a symmetric state, like a perfectly sharp pencil balanced on its point. This state was unstable, and as the cosmos cooled, the field settled into a stable, non-zero value everywhere, breaking the initial symmetry. This transition is what granted mass to fundamental particles like electrons and quarks. The more a particle interacts with this field, the heavier it becomes, while particles like photons, which do not interact, remain massless. The confirmation of this theory came with the monumental discovery of the Higgs boson at CERN in 2012. This particle is not the field itself, but a localized ripple within it, much like a splash in water proves the existence of the lake. Detecting this ripple required the immense energy of the Large Hadron Collider, essentially recreating the conditions of the universe a trillionth of a second after the Big Bang. This discovery completed the standard model of particle physics, but it also opened a door to deeper mysteries. The Higgs field is likely not alone. Similar scalar fields are thought to have orchestrated other cosmic dramas. The same type of mechanism, where a field settles into a new state and breaks a symmetry, is believed to have driven the electroweak phase transition. In the universe's first moments, the electromagnetic force and the weak nuclear force were unified as a single electroweak force. As the cosmos cooled, a scalar field underwent symmetry breaking, splitting this single force into the two distinct forces we observe today. This very phase transition, occurring out of thermal equilibrium, might have provided the precise conditions necessary for baryogenesis, creating the critical matter-antimatter imbalance that allowed our universe to exist. The influence of scalar fields may extend even further. The inflaton field, which powered the exponential expansion of cosmic inflation, is theorized to be another scalar field. Some models even suggest that dark energy itself could be the subtle effect of a dynamic scalar field, like quintessence, slowly evolving and pushing the universe apart. This connects to the startling idea of false vacuum decay. Our universe's Higgs field may exist in a metastable state, a shallow energy valley that is stable for now, but not the absolute lowest possible state. A random quantum event could theoretically create a bubble of true vacuum where the laws of physics are completely different, expanding at the speed of light and rewriting reality. The search for evidence of supersymmetry is also deeply tied to scalar fields, as the theory predicts a whole family of partner particles to the Higgs, which could help explain the perplexing fine-tuning of the vacuum energy. How would our understanding of reality shift if we knew the laws of physics were not eternal constants, but temporary artifacts frozen into place by the whims of a scalar field? This question of how fundamental information is encoded and stored finds a radical answer in the principle of holography. A black hole's event horizon seemed to be the one place where information could truly vanish, swallowed by infinite gravity and lost forever. This was the information paradox, a crisis at the heart of physics that threatened to unravel our understanding of reality. But from this puzzle emerged one of the most radical ideas in modern science, the holographic principle. It proposes that our three-dimensional reality, with all its stars, galaxies, and forces, might be a projection from a two-dimensional surface, a cosmic illusion as vast as the universe itself. Physicist Juan Maldacena captured this profound shift, stating, The holographic universe implies that what we see is a shadow of deeper, simpler laws. The theory's roots lie in string theory, specifically through a mathematical discovery known as the ad-SCFT correspondence. This framework demonstrates a perfect equivalence between a theory of gravity operating in a volume of space and a quantum field theory without gravity living on that volume's boundary. It is like discovering that the entire complex story of a movie is completely encoded on the flat surface of the film reel. In this view, gravity and the other forces we experience are not fundamental, but emergent phenomena, properties that arise from the intricate processing of information on a distant, lower-dimensional screen. This perspective offers a stunning resolution to the black hole information paradox. When matter falls into a black hole, its information is not destroyed. Instead, it is perfectly scrambled and encoded onto the event horizon itself, the black hole's two-dimensional surface. The entropy of a black hole, a measure of its hidden information, is proportional to the area of its event horizon, not the volume it contains. This was the crucial clue from Jacob Bekenstein and Stephen Hawking, a hint that information capacity is bound by surface area, not volume, a core tenet of the holographic principle. This idea even addresses the troubling singularity at a black hole's heart. The infinitely dense point may be a mathematical artifact, a sign that our description of gravity breaks down. In the holographic view, the true, information-based description of the black hole resides safely on its boundary, where the laws of quantum mechanics remain intact and the singularity is effectively smoothed away. The implications stretch to the cosmos itself. Some theorists have calculated that all the information contained within our entire observable universe could theoretically be encoded on a spherical shell at its boundary. Every event, every particle, every thought you have ever had could be represented by bits of data painted onto the farthest surface of reality. This leads to a deeply philosophical question. If our perceived reality is a holographic projection, a consequence of information processing on a cosmic scale, what does that say about our own experience of free will and destiny? Are our choices our own, or are they simply the unfolding of a script written on the edge of the universe? This question naturally draws our focus inward, to the one instrument we use to observe this projected reality, the human mind. Our own awareness might be the most fundamental tool of cosmic creation. Does the universe, in some profound sense, require a conscious observer to bring it into being? This is the startling intersection of consciousness and cosmology, a place where we are no longer just passive inhabitants but potential architects of reality itself. The physicist John Archibald Wheeler proposed this radical idea, suggesting we are participants in bringing into being not only the near and here but the far away and long ago. This concept is deeply intertwined with the anthropic principle, which attempts to explain why the universe seems so exquisitely fine-tuned for our existence. The weak version of this principle states that the universe we observe must be compatible with the conscious life that observes it. We should not be surprised to find ourselves in a universe with constants that allow for stars, planets, and life, because in a universe without those conditions, we would not be here to ask the question. It is a simple, almost tautological statement, yet it carries immense weight. The strong anthropic principle, however, takes a far more active role. It suggests that the universe must have properties that inevitably lead to the emergence of conscious observers. In this view, observers are not just accidental byproducts, but a fundamental requirement for the cosmos to achieve its full reality. This idea finds a strange echo in the quantum world, particularly in the famous double-slit experiment. When a single particle, like an electron, is fired at a barrier with two slits, It behaves as a wave, passing through both openings and creating an interference pattern on the detector screen. But the moment you place a device to observe which slit the electron goes through, the wave-like behavior vanishes. The particle acts like a single, localized object. The very act of measurement, of observation, seems to force the particle to choose a definite state. This is the measurement problem, the puzzling link between the quantum realm and the world of definite outcomes we experience. The strong anthropic principle pushes this further, implying that a vast, unobserved universe is a blur of quantum potential, and it is the arrival of conscious minds that crystallizes it into the concrete reality we share. The fine-tuning that makes this possible is breathtakingly precise. If the cosmological constant were slightly larger, the universe would have expanded too rapidly for galaxies to form. If the force of gravity were minutely stronger, stars would burn through their fuel in millions of years instead of billions, leaving no time for life to evolve. If the strong nuclear force were a few percent different carbon atoms, the basis of life as we know it would never have been forged in stellar cores. We live on a razor's edge of physical law. Critics argue that the anthropic principle is not a scientific explanation at all, but a philosophical retreat. They point to the multiverse as a more testable solution. In an infinite landscape of parallel universes, each with randomly different constants, it is no surprise that we find ourselves in one of the rare habitable ones. Our universe is not fine-tuned, we are simply the lucky winners of a cosmic lottery. Yet the question remains, does our observation actively select which universe we are in from a sea of possibilities? Are we, through the simple act of perception, co-creating the cosmos, solidifying one specific timeline from a fog of quantum probabilities? The laws we take as immutable may be a collaborative project, a dialogue between the universe and the minds that have emerged to witness it. What responsibility does that place upon us, the temporary custodians of this conscious gaze? A new generation of eyes is now turning toward the sky, instruments of such sensitivity they will listen for the echoes of creation itself. The Laser Interferometer Space Antenna, or LISA, is a future mission that will open an entirely new window on the cosmos. Unlike its ground-based cousins, LISA will consist of 3 spacecraft flying in a perfect triangle millions of kilometers apart, connected by laser beams. This colossal observatory in the void will detect the low-frequency hum of gravitational waves from events we can only dream of today, the mergers of supermassive black holes at the hearts of ancient galaxies, and the faint, persistent rumble from the cosmic strings that may have seeded the first structures. Astronomer Wendy Friedman captures the promise of this era, stating that next-generation telescopes will map the universe in unprecedented detail, uncovering the forces that shape our destiny. This is not the work of a single machine, but a coordinated assault on the unknown by a fleet of new observatories. The Vera C. Rubin Observatory, with its immense 3.2 billion pixel camera, will repeatedly scan the entire southern sky, creating the deepest, widest movie of the universe ever made. It will watch for the subtle warping of starlight by dark matter, mapping its invisible distribution in 3 dimensions and potentially catching the fleeting glow of actions decaying in the halos of galaxies. Meanwhile, the European Space Telescope Euclid is already surveying billions of galaxies to measure the history of cosmic expansion with breathtaking precision, tracing how the push of dark energy has changed over billions of years. On Earth, in the pristine cold of the South Pole and the high Chilean deserts, the CMB S4 project will deploy 500,000 detectors to stare at the cosmic microwave background. Its goal is to find the faint, curling B-mode patterns, the signature of primordial gravitational waves, a direct glimpse of the inflattened field that set the entire cosmic story in motion. These tools will be complemented by the Nancy Grace Roman Space Telescope, a wide-field infrared observatory that will perform its own monumental dark energy surveys. It will use 3 independent methods tracking the growth of galaxy clusters, measuring the bending of light from weak gravitational lensing, and discovering thousands of distant supernovae to pin down the nature of dark energy with an unassailable weight of evidence. The search for the particles themselves is also reaching a fever pitch. Deep underground, in laboratories shielded from cosmic rays, ultra-sensitive experiments are waiting for the once-in-a-universe bump of a weakly interacting massive particle. Vats of liquid xenon are kept in total darkness, their sensors poised to capture the tiny flash of light and charge if a dark matter particle ever interacts with an atom. Other teams are building intricate resonators to catch the conversion of an action into a faint microwave photon in the presence of a powerful magnetic field, a whisper from the quantum sea that could solve the mystery. These observational and experimental campaigns are powered by another hidden architect, the silicon brain of the supercomputer. Immense cosmological simulations run on the world's most powerful machines, tracing the journey of trillions of virtual particles from the first quantum fluctuations to the grand cosmic web of today. By comparing these simulated universes to the maps created by our telescopes, we can test our theories of dark matter and dark energy with a rigor never before possible. What ancient secrets buried in the data streams of these new machines will finally reveal the identity of the hidden architects and rewrite the story of our cosmic origins? This empirical march forward is inextricably linked to a parallel revolution in theoretical thought. Physics is a puzzle whose final picture remains maddeningly out of view. 2 grand frameworks have emerged in the quest to complete it, each offering a radically different vision of reality's deepest foundations. String theory and loop quantum gravity represent our most ambitious attempts to unite Einstein's gravity with the quantum world, to find a single set of rules governing everything from the vast cosmos to the tiniest subatomic flicker. String theorist Brian Greene framed the core idea by saying, "String theory suggests that particles are tiny vibrating strings with hidden dimensions shaping reality." In this view, the fundamental constituents of the universe are not point-like dots, but unimaginably small, vibrating loops of energy. The different vibrational patterns of these strings give rise to the entire particle zoo, from electrons to quarks. Much like different vibrations of a violin string create distinct musical notes. The mathematics of this elegant idea, however, demands a startling price: the existence of extra spatial dimensions beyond the 3 we experience. These dimensions are thought to be curled up into intricate, microscopic shapes known as Calabi-Yau manifolds. The specific geometry of these hidden folds would determine the properties of particles and forces in our visible universe, effectively writing the laws of physics into the fabric of space itself. This framework expands into M-theory, a unifying umbrella that suggests strings are just one manifestation of more fundamental objects called branes, short for membranes. Our entire universe could be a 3-dimensional brane floating in a higher dimensional bulk, with gravity perhaps leaking between branes, a concept that could offer novel explanations for dark matter. Yet string theory faces a profound challenge: the landscape problem. The mathematics allows for a staggering number of possible stable configurations for those extra dimensions, perhaps 10 to the 500 different versions, each with its own laws. This vast landscape makes specific predictions for our universe incredibly difficult, leading some to ask if we simply reside in one bubble among a near-infinite multiverse where any law is possible. In stark contrast, loop quantum gravity takes a different path entirely. It does not propose extra dimensions or vibrating strings. Instead, it suggests that space and time themselves are not smooth and continuous, but are woven from a fabric of tiny, discrete loops, a network of individual quanta of spacetime. Picture the cosmos not as a perfectly smooth sheet, but as a fabric woven from a billion tiny, interwoven threads. This granular structure becomes apparent only at the minuscule Planck scale, but its implications are cosmic. This approach yields stunning predictions for the most extreme environments. In loop quantum gravity, the center of a black hole is not an infinitely dense singularity, but a portal to another region of spacetime, a cosmic bridge rather than a dead end. Even more profound is its vision of the Big Bang. The theory suggests that the collapse of a previous universe could have reached a maximum density and then rebounded in a big bounce, implying our universe may have been born from the death of a cosmos that came before. This idea of a cyclical universe without a true beginning or end offers a breathtaking alternative to a single creation event. So which of these competing blueprints will ultimately describe the hidden architecture of our cosmos? Will it be the tiny, vibrating strings in a folded, higher-dimensional space, or the granular, quantized threads of spacetime itself? The answer may not come from pure thought alone, but from the relentless number crunching of silicon minds as computational cosmology begins to simulate realities governed by these very rules. A virtual universe began with a single snapshot of data. Inside a supercomputer, 1 trillion particles were set in motion, each one representing a clump of dark matter, their collective gravity the only rule. This was the Millennium Simulation, one of the most ambitious computational experiments ever conceived. Over weeks of processing, it watched as gravity worked its invisible magic, weaving those particles into a vast, cosmic web of filaments and voids that perfectly mirrored the one we observe in our real sky. This is the power of computational cosmology, the discipline of using supercomputers and sophisticated algorithms to recreate the entire history of the universe, from its first quantum whisper to the grand galactic metropolises of today. As cosmologist Carlos Frenk explains, simulations are our digital telescopes, letting us watch the universe grow from quantum seeds. These are not simple animations. They are rigorous mathematical experiments that test our deepest theories about dark matter and dark energy. The most advanced simulations are known as n-body simulations, but they go far beyond just tracking gravity. They incorporate the complex physics of hydrodynamics, which models how cosmic gas flows, heats, and cools. They include feedback processes where exploding supernova and ravenous black holes inject tremendous energy back into their surroundings, shutting down star formation or blowing gigantic bubbles in intergalactic space. Projects like Illustris TNG have pushed this even further, creating virtual universes where simulated galaxies exhibit realistic shapes, sizes, and colors, matching our telescopic surveys with uncanny accuracy. These digital laboratories allow us to perform experiments we never could in reality. We can watch a dark matter halo, that invisible gravitational well, slowly pull in ordinary gas over billions of years. We can see the gas condense, fragment, and finally ignite into the first stars, revealing the intricate timescales of galaxy formation. We can even switch off dark energy in a simulation and watch how the cosmic web fails to form correctly, or dial its strength up and witness the universe tear itself apart prematurely. The sheer volume of data these simulations produce is so immense that cosmologists are now turning to machine learning. Artificial intelligence algorithms are trained to sift through the simulated data, identifying subtle patterns and relationships that would take a human researcher a lifetime to find. They can instantly compare 1,000 different virtual universes, each with slightly different physical laws, against the painstaking maps from observatories like Euclid and the Vera Rubin Observatory, homing in on the model that best matches our own. This leads to a profound question. If our simulations become accurate enough to perfectly retrodict our past, could they one day be used to forecast our ultimate fate? Could we run the simulation forward, factoring in every known force and particle, to see if the cosmos ends in a big freeze, a big rip, or a silent fade into nothingness? The power to not just understand but to predict the entire cosmic destiny carries its own weight, a responsibility that moves us from pure discovery into the realm of profound choice. If the grand architecture of the cosmos is predetermined by invisible forces, where does that leave our own small choices? Does a universe governed by hidden architects diminish our free will, or does it instead elevate our existence, connecting our brief conscious moment directly to the cosmic machinery itself? These are not new questions, but they are sharpened by our modern understanding of dark matter and quantum fields. Philosopher Nick Bostrom observes that understanding cosmic forces challenges our place in the universe, urging humility and curiosity. This tension between determinism and free will is at the heart of the matter. If the distribution of dark matter dictated where the first galaxies would form, and if quantum fluctuations set the initial conditions for everything, is the entire cosmic story, including our own, already written? Or does our emergent consciousness introduce a genuine wild card, a novel form of causality within the established physical laws? The anthropic principle adds another layer to this debate. If our universe is just one of a near-infinite multiverse, fine-tuned for life by sheer chance, does that rob our existence of a grand, singular purpose, or does it make our specific reality all the more precious and rare? This perspective inevitably influences our ethical considerations, particularly toward our own world. The Copernican revolution first displaced us from the center of the universe, a profound blow to human ego. Yet it also expanded our horizons, teaching us that we are part of a much larger system. Today, knowing that our planet is a fragile oasis in a cosmos mostly shaped by invisible forces, creates a powerful impetus for environmental stewardship. If Earth is a rare, vibrant anomaly in a vast, dark sea, our duty to preserve it becomes a cosmic responsibility, not merely a local one. This sense of responsibility extends to the technologies we might one day develop. The potential to harness the quantum vacuum or manipulate dark matter carries immense promise, but also profound risk. Could a misunderstanding of these fundamental forces lead to a catastrophic miscalculation, a chain reaction we cannot control? Our ethical duty, then, is to pursue this knowledge with profound caution, pairing our growing power with even greater wisdom. And just as the revelation of a heliocentric solar system inspired centuries of art, music, and literature, so too does our current cosmic narrative. The image of a holographic universe or of strings vibrating in hidden dimensions provides a new wellspring of inspiration, challenging artists to give form to the formless and to make the invisible felt. How should humanity, armed with this fragile and incomplete knowledge, steward its understanding of the cosmic architects? The answer may lie in balancing our drive for mastery with a deep-seated reverence for the mysteries that remain, recognizing that our quest for meaning is itself a fundamental force shaping our collective destiny. This search for meaning, however, is not a singular Western endeavor. It is a story told in countless ways across human cultures, each with its own unique interpretation of the hidden forces that guide the stars. Atlas, the Titan of Greek legend, did not merely hold a flat earth upon his shoulders. He bore the celestial sphere, the entire weight of the heavens, a mythic echo of the invisible dark matter halos that now, in our scientific understanding, hold galaxies intact. Across the globe and throughout time, human cultures have looked to the stars and sensed the hidden architects at work, personifying these forces into gods, spirits, and cosmic beings. In Hindu cosmology, the entire universe exists within the dream of Lord Vishnu, a cyclical vision of creation and dissolution that mirrors our own scientific models of a potentially infinite multiverse. Mythologist Joseph Campbell captured this profound connection when he said, "Myths are public dreams, dreams are private myths, both exploring the unseen structures of reality." These ancient systems were not primitive guesses. They were sophisticated frameworks for understanding a cosmos filled with powers beyond direct perception. The Chinese concept of the Tao represents the fundamental, ineffable flow of the universe, a force that cannot be seen or named, yet gives rise to all of existence, much like the quantum fields that underpin our reality. In Navajo traditions, spiritual forces and holy people established the cosmic order, guiding the patterns of the stars and the winds, a worldview that assigned purpose and consciousness to the invisible dynamics we now chart with telescopes. These narratives served a dual purpose. They provided a coherent explanation for the cosmic order, explaining why the sun rose and the seasons turned, and they rooted humanity within that order, giving our lives meaning within a vast, animated cosmos. This mythological impulse directly influenced early astronomy, where the quest to understand the gods drove meticulous observations of planetary motions, laying the groundwork for the science of celestial mechanics. Today, as we grapple with the profound mysteries of dark energy and the quantum vacuum, we find ourselves asking a similar set of questions about the unseen fabric of reality. The relentless push of dark energy, for instance, finds a curious parallel in some creation myths that speak of a great wind or breath that initiated and sustains the expansion of the world. Do these ancient stories, born from millennia of human wonder, hold intuitive clues to the nature of the hidden architects we are only now beginning to measure? Perhaps they point less to specific physical laws and more to a universal human intuition that the true rulers of reality are veiled from our ordinary sight. This deep-seated need to give form to the formless has not ended with the age of science. It has simply found new canvases in the art and media of our modern world. The film Interstellar did not just imagine a black hole, it visualized one with such scientific precision that its rendering of Gargantua became a research paper in its own right. Guided by physicist Kip Thorne, the filmmakers translated the invisible forces of general relativity into a breathtaking, swirling disk of light, making the warping of spacetime a visceral, emotional experience for millions. This is the power of art and media to bridge the gap between abstract equations and human perception, giving tangible form to the hidden architects of the cosmos. Artist Leah Halloran captures this mission perfectly, stating that art can make the invisible visible, giving form to dark matter and quantum fields. Her own work uses cyanotype prints to map dark matter halos, transforming gravitational data into stunning, deep blue constellations that hang in galleries, allowing us to feel the presence of the unseen mass that holds our galaxy together. This fusion of science and creativity extends far beyond the cinema screen. The vast data sets from the Sloan Digital Sky Survey, which catalog millions of galaxies, are not just for research. They are used to create immense, interactive installations where you can literally walk through the cosmic web, watching filaments of galaxies sparkle around you, making the scale of dark matter's architecture intuitively understood. Virtual reality experiences now let you stand on the edge of a simulated black hole or navigate the folded dimensions of a Calabi-Yau manifold, turning the most esoteric theories into explorable landscapes. Documentaries and podcasts act as vital translators, narrating the epic of cosmic inflation or the mystery of neutrino oscillations with a clarity and passion that textbooks rarely achieve. They turn the latest findings from the Event Horizon Telescope or the James Webb Space Telescope into a shared cultural event, a story in which everyone can participate. The educational impact is profound. A child who sees the Hubble Space Telescope's pillars of creation, that majestic tapestry of gas and dust where stars are born, does not just see a pretty picture. They witness the result of gravitational collapse and stellar feedback, a dynamic process made beautiful and unforgettable. These images, blending empirical truth with sublime beauty, spark a curiosity that can define a lifetime, drawing new minds toward the quest to understand our cosmic destiny. How does this artistic translation deepen our connection to the cosmos's hidden architects? It moves them from the realm of cold data into the space of human wonder, making the dark energy that pushes the universe apart not just a parameter in an equation, but a character in our own story. This creative engagement naturally fosters the next generation of explorers, whose first glimpse of the universe's wonders will come not from a lecture, but from a screen, a canvas, or a virtual world. A child stands in a backyard, her face tilted toward a sky salted with stars. In that silent gaze is the same primal wonder that has driven every discovery about the hidden architects of our universe. Educator Neil deGrasse Tyson beautifully captured this, saying the universe is a classroom without walls, inviting us to learn its secrets. This innate curiosity is the engine of cosmology, and nurturing it through science education is how we empower the next generation to solve the mysteries we cannot. The journey to understand dark matter and dark energy begins not in a distant laboratory, but in a child's first question about the night sky. To answer that call, we have built pathways that make the cosmos accessible to everyone. Planetarium shows transform abstract concepts into immersive experiences, where you can fly through the cosmic web and watch dark matter halos sculpt galaxies in real time. Citizen science projects like Galaxy Zoo invite anyone with an internet connection to become a cosmic cartographer, helping professional astronomers classify millions of real galaxies, contributing directly to our maps of the invisible universe. Online courses and public lectures break down the barriers of the lecture hall, demystifying quantum fields and inflationary theory for a global audience. The goal is inclusive access, ensuring that the tools for cosmic exploration are not limited by geography or background. Museums with interactive exhibits and programs like the Universe in a Box kits used in classrooms allow students to physically model cosmic evolution, tracing the journey from the Big Bang to galaxy formation with their own hands. This early exposure is critical, as it plants the seed that can grow into a career in astrophysics or computational cosmology. When a young mind sees themselves as part of this grand story of discovery, they gain the confidence to pursue the questions that still baffle the greatest minds. How can we ensure that every person, regardless of where they are born, has the opportunity to pick up these tools and add their own chapter to the human story of cosmic exploration? This question leads us from the collective mission of education to the deeply personal reflections that such vast knowledge inspires. The same quantum tremors that seeded the Andromeda Galaxy might also ripple through the intricate pathways of your own mind. Every thought you form, every memory you recall, is a symphony of electrical impulses, a dance of particles whose very existence was forged in the hidden architecture of the cosmos. Your life is not separate from these forces, you are a living expression of them. The gravity that holds you to the Earth is the same force that binds galaxies into clusters. The sunlight that warms your skin is energy released from nuclear fusion, a process dictated by fundamental constants set at the dawn of time. The poet Maya Angelou beautifully expressed this profound unity, writing, "We are more alike than unalike, my friend, connected to the cosmos in every breath." Every atom of oxygen you inhale was fused inside a massive star that lived and died long before our sun was born. The iron in your blood was forged in the heart of a supernova, its explosive death seeded by the gravitational pull of invisible dark matter. Understanding this deep interconnection can be a source of profound personal transformation. It can foster a sense of awe that puts our daily worries into a grander, more manageable perspective. The stress of a traffic jam or a difficult day at work begins to fade when held against the backdrop of a 13.8 billion-year cosmic drama. This perspective does not diminish our lives, it enriches them, reminding us that we are participants in an epic story, a story whose chapters are written by dark energy, quantum fields, and the relentless flow of time. This cosmic viewpoint can also be a powerful wellspring for creativity, inspiring new ways of thinking and problem-solving by connecting us to the fundamental patterns of the universe. You can engage with this reality in simple, tangible ways. Go outside on a clear night and simply look up, practicing the ancient art of stargazing without any telescope at all. Read a book on cosmology written for a general audience, allowing the ideas to settle in your imagination. You might even try a moment of quiet meditation, focusing on the breath that connects you to the atmosphere, which connects you to the planet, which orbits a star, which moves within a galaxy, all held in the embrace of an invisible cosmic web. How does knowing that your very body is built from stardust assembled by forces you cannot see change the way you move through your day, how you face a challenge, or how you cherish a moment of joy? The universe is a single, magnificent tapestry, its story woven from threads we can never see. Dark matter provides the underlying warp, the invisible foundation that holds the galactic threads together. Dark energy is the relentless weft, stretching the cosmic fabric wider with every passing moment. Gravity is the master weaver, sculpting the intricate patterns of planets and stars from the subtle wrinkles left by ancient quantum whispers. Physicist Lisa Randall captured this profound collaboration perfectly, saying the cosmos is a dance of visible and invisible partners, each essential to the whole. These architects do not work in isolation, they are locked in a continuous, dynamic feedback loop. The gravity of a dark matter halo pulls in the gas that forms a galaxy, whose central supermassive black hole then feasts and erupts, pouring energy back out that can heat the surrounding dark matter and stifle further star birth. This cosmic conversation is our oldest photograph, the cosmic microwave background. Its mottled patterns of hot and cold are a frozen moment from the universe's infancy, a snapshot of quantum fluctuations amplified by inflation and then gravitationally sculpted by both dark and visible matter. To explain the full choreography of this dance, scientists are exploring radical new theories. Some propose that our understanding of gravity itself is incomplete, that modified Newtonian dynamics, or MUND, could explain galactic rotations without the need for dark matter, though this struggles to account for the evidence from galaxy clusters. Others suggest that spacetime and gravity are not fundamental, but emergent properties, arising from the collective behavior of countless quantum bits, much like the temperature of a room emerges from the frantic motion of invisible molecules. The grand quest is for a single narrative that can seamlessly unite the quantum realm with the cosmic stage, a theory of everything that explains why these specific architects, with their precise strengths, came to build our particular reality. We have mapped their individual contributions, but the symphony of their interactions is still being deciphered. What new, even more fundamental architect might we discover when we finally learn to listen to the entire orchestra playing as one. Our journey through the invisible foundations of reality reveals a cosmos crafted by unseen hands. From the gravitational anchor of dark matter to the relentless push of dark energy, from the quantum tremors that seeded galaxies to the scalar fields that grant particles mass, these hidden architects have collaborated for billions of years to build the universe we call home. They wrote the blueprint in the cosmic microwave background, they sculpted the vast cosmic web, and they now dictate our ultimate cosmic fate, whether it ends in a silent freeze or a dramatic tear. This knowledge does more than advance science, it deepens our own sense of place within this grand design. We are not mere spectators, we are active participants, our very consciousness a product of these precise and ancient forces. Carl Sagan's timeless words remind us that somewhere, something incredible is waiting to be known. The search for these hidden architects is far from over, and every new discovery adds another thread to the magnificent tapestry. We would love to hear which of these invisible forces captures your imagination the most. Is it the ghostly pull of dark matter holding galaxies together, or the enigmatic push of dark energy driving them apart? Share your thoughts in the comments below about how this cosmic perspective changes your view of reality. If you want to continue exploring the deepest mysteries of space with us, be sure to subscribe. The next time you find yourself under a starry sky, look up and remember the invisible architecture at work. We are all living within a universe designed by hidden architects, and the greatest discoveries are